All right. It is 1:30. I'm going to get started here. Today I have two urgencies. One urgency to get started as early as possible is because I forgot to bring my adapter, so I'm running on battery power only. And if I run out of juice, then there will be no more recording. I can still teach. Okay, I don't need my computer nor the network to teach, but there won't be any recording, unless you guys are recording it. Huh? But you won't have the software that I need.
I got XO one.
Oh, you got what?
XO.
XO?
Microsoft Technique.
Oh, okay. So possibly, I'm hoping that with 25% of my battery power left, I have enough juice to do it. I think it does. Because I'm not going to use anything that's particularly power hungry. If anyone has a USB-C charger, that would help too. But I need is that how much juice is that? Oh, that would do it, if you don't mind. Thank you. Just remind me to return this to you. Right. There we go. All right, it's charging. Thank you. Even a regular 5 volt at 2 amps would help, because it would just kind of slow down the discharge. So even that would kind of make sure that we can last until the end of it will last. Very good then. Okay. So just a few announcements. For the homework assignments, you might get a email from Canvas saying that no submission. Okay, if you already have shared a document with me, you can ignore that. Okay, because it simply means that the first pass of me going through Canvas could not find a link as a submission from you. But if you have already shared with me, my Gmail account would have a message that says, this person has shared a document with me, and I will go back and go through that list, as a second pass. Okay. If you see a message that says, document not shared, also it's going to be okay. Just go ahead and share the document with me. Don't modify the content, just share. Yep.
So when I go into it, it says I shared it with you,
Uh-huh.
but I still got the document not shared. I just checked the email too.
Okay. So did you share with my W0006887 at apps.lostreals.edu? That is weird. Okay. Okay, maybe later, I can take a look. That is kind of strange, because when I try to open it from Canvas, it says, it could not open it. So I will look into that. All right. So what we'll do today is to continue our discussion on Tuesday about functions, inverse of a function, and how that is actually useful when we need to analyze the logic of a program and see if we can prove that an algorithm is correct mathematically. So that's kind of the context of all of this discussion. It's difficult for me to give you homework assignments at this point, because I do want to kind of go over all the concepts first. Then I can give you assignments where you can kind of exercise all of the concepts that we have talked about. Okay, so at this point, your assignment is kind of more or less, just reading the material and making sure that you understand the material after each class. So that's going to be the important part. All right. So instead of using a text editor, which is not very good with mathematical notation, I'm going to use the tablet part and just handwrite stuff. Okay. So this is not for you guys. This is for cisp300. I will see many of you, hopefully, in about 2 semesters, because I don't teach CISP 360, which is the prerequisite of CISP 310. So when you take cisp300, you will most likely see me again, because as far as I know, I'm the only person teaching that class on this campus. Yes, there are people who escaped me by going to other campuses, in case that's what you're thinking. All right, so getting to functions and inverse functions, okay? So we'll start with just the notation of a normal, function. So if I say, f of x is defined to be, say, x plus 1, okay? Does everybody understand this notation? Function f is defined to be x plus 1. So anytime I refer to f of something, I'm simply saying add 1 to it. Is that good? Okay. So this means f of 20, for instance, is just 20 plus 1, which turns out to be 21. Is that okay? So x has no special meaning. When we define the function f, this x here, which we know as a parameter later in this class, is just a placeholder. It's a variable, it's a placeholder. It simply says applying function f to something is that something plus 1. And that's all it says. Is that good? All right. So in this class, we won't deal with anything that's too complicated. I would say, addition, subtraction, multiplication, and division is kind of all we do in this class. So there won't be any sine, cosine, taking derivative of something, and so on and so forth. So it's not, we simply borrow the notation of a function for discussion purposes, okay? All right, so if I define, in this case, f inverse of x, so this notation, once I define what f is, when you see f superscript -1, we are referring to what we call an inverse function, okay? This is an inverse function of f of x. So what do you think that should be? If f of x is adding 1 to something, to x, how do I undo that? -1, right? Yeah, x minus 1. Okay, so this is x minus 1. And the idea of an inverse function is if you apply a function on top of the inverse function of something, you get that something back. If you apply the inverse function on top of the function on something else, you also get whatever the original thing back, okay? So I know it sounds really confusing. Writing it out makes it less confusing, okay? So this is what I'm going to do. So if you apply the function f to the inverse function of f to something, let's figure out what this is going to do. So at this point, you get two choices. You can either apply f first, or you can apply f inverse first. Either way is okay. There's no right or wrong in this case, because they would expand out to exactly the same thing. So my usual inclination is to apply the innermost first. So I'm going to say, oh, this is the f applied to x minus 1. Do we have any questions about this? Yes? No? This is all good? Okay. Yes?
Is it like math where you do the parentheses first, or you said it doesn't matter?
It does not matter in this case because we're only expanding a function into its original form. So I will show you. The other way works out just fine too. Okay. So, but in this case, I'm expanding f inverse of x to x minus 1 first. Is that okay? That's exactly how f inverse of x is defined. So I'm just using x minus 1. Now I expand f on top of this. So now it becomes x minus 1, the whole thing plus 1. Now, that pair of parentheses are not needed. I only put it there to emphasize that whatever this thing is really just whatever that thing is inside the parentheses when we apply f. That's why I put the extra pair of parentheses, just to emphasize that where x minus 1 came from. Is that okay? So, for those of you who know algebra, you can see that, hey, we can dissolve that parentheses, that pair of parentheses, and then we just get x back. Is that okay? So we can try the other way, which is to apply the outer function first. So that will give us f inverse of x plus 1, right? Because I said I apply f first, so whatever all f does is to add 1 to whatever the parameter is. So it becomes just the parameter plus 1. Is that okay? So now we can expand what is f inverse of x is, which is x minus 1. So now we get back x minus 1 plus 1, which once again is x. So this shows you that it doesn't really matter when you apply a function on top of another function, whether you apply the outermost first or you apply the innermost first, they should boil down to exactly the same thing. Are we doing okay so far with this? Okay. Okay, so what if I do something like this? What if I apply f inverse to f of x? Well, let's check it out. So once again, the top one is going to be applying the inner function first. So this will become f inverse of x plus 1, right? And what that becomes is x plus 1, the whole thing minus 1, which also turns out to be x. Yes? If I apply the function in the outermost first, then I end up with f of x minus 1. But that also turns out to be just x plus 1 once I expand f minus 1, and that turns out to be x. So this is kind of cool because it says, it doesn't matter whether you are applying f on top of f inverse or whether you're applying f inverse over f. They boil down to the same thing. We still get x back. So are we doing okay so far with this stuff here? To relate, f inverse to the identity function, which is basically just saying we end up doing nothing. Is that okay? How many people have watched? What is the name of that show? It's Amazon. It's a short series. It's about a demon and a demon and an angel.
Good Omens?
Good Omens. That's it. It's about, okay, so you guys would think, what does this have anything to do with good omens, right? Think of this as the devil and that as the angel. The argument between those two is, well, if I do my job and you do your job, then we end up doing absolutely nothing. That's a net of 0. So why don't we just do nothing? Because if we do our jobs, it is as if we don't do anything. So if we don't do anything, it's just the same as far as the world is concerned. But then we have all the spare time to do all the other things, like wine tasting for the demon and going to restaurants for the angel. If you haven't watched that show, it's really funny. Okay? But when you do watch that show, think of one of them as function f and the other as the inverse function. Then you will totally remember this whole discussion. I mean, David Tennant is very convincing. Yes?
So they kind of cancel each other out?
Yes, they do. That's the idea. So they both got, quote unquote, lazy because they said, if I do my job and you do your job, we end up doing nothing because we cancel out. So why don't we just decide to do nothing? Each would do nothing. Then the world wouldn't know the difference. Yep.
They just cancel each other out. Why? What's the point of putting a function within another function?
We'll talk about this. Okay. All right. So now we tie this into the discussion of pre and post conditions. Okay. So here is a precondition. Okay. So let me give you a statement first. Okay. So this statement looks really abstract because we are working on line n. So you go like, where's n? It can be any line number, okay? We have a variable. I'm just going to call the variable v here. And v is updated by a particular function f applied to v, okay? This looks awfully abstract, right? Because I'm not even telling you what f is. F can be v plus 1, can be v divided by 2, can be 3 times v. We don't know what f is, Okay, all we know is the way we update this variable v here on line n is it is a function of v itself, and we also know that that function has an inverse. That's the only thing we need to know is f is a function and it has an inverse. Is that okay? So at this point, it doesn't seem like, how is this going to help us analyze the pre and post condition of this entire thing? All right. So for the pre and post discussion, I kind of need to use an example, okay? So the precondition of n, let's say that it is, I really don't want to use what we call a predicate, but I'm trying to think of, can I avoid that? Okay, here. Okay, so I'm gonna just write it out without using the concept of a predicate, but it really is a predicate. Okay. So I'll just say what we know about v. Okay, that is true. Is that okay? So this is parameterized by variable v, okay, because it is a whole big, huge, long Boolean expression that has v sprinkled around, okay? But exactly what it is, we don't care. We don't need to know. Is that okay? Now we try to answer the question, what about the post condition then? Okay, what about post of n? The post condition of line n. What would that look like? Now, since we talk about function and inverse function, the first thing you would suspect is, I think that inverse function is going to be useful somehow, right? Then the second thing is, probably we still need to retain most of what we know about v. But v is no longer the same as before line n executes, right? Because line n, the job of line n is to say, do some computation, on n, using f of n, whatever that value is, use it to update the variable n. So, variable v. So that means, v has changed. But can we undo that change so that we say, all of those things that we knew about v is actually still true, but it is true about what? It's true. Okay. Let me see if I can come up with a concrete example, in real life, so that you guys can understand this concept. So, okay, here's the one. Okay, so let's say you know a toddler, okay, or a young kid, and last time you saw the kid, the kid was at the same height as a table. Okay, so we'll just say that this is the table. So last time you saw this nephew or kid of whatever kid is that person is the same height as the table. Okay, and then you are told by the parent of the child that that kid grew by 2 inches this year. Okay? And now we know, and then the parent of the kid also told you and say, oh, Timmy is now, I'm just guessing, 36 inches tall. Okay? The question is, can you figure out how tall Timmy was last time you saw him? Okay, let me re-express the question, okay? You saw Timmy last year. Timmy was the same height as the table. But you did not measure, so you did not know exactly how tall Timmy was. The only thing you knew was he was as tall as the table. We good on that? This year, you got a phone call from Timmy's parent. And in the conversation, Timmy's parent said, Timmy grew a lot this year. He is now 32 inches, 30, what was the number I chose? Huh? 36. He's now 36 inches tall, and guess what? He is now 2 inches taller than the table. Okay? So can you figure out how tall Timmy was last year? And that was 34 inches, right? And how did you know that? How did you figure that out? Right. Because but this is okay, so think of Timmy's height as variable x. Okay? The fact that we know Timmy was the same height as the table was what we know about v. Is that okay? Function f is Timmy growing by 2 inches. Okay? And the new value of v is 36 inches. Is that okay? So we apply the inverse function because the function itself is saying grow by 2 inches. That's the function. And that ends up at 36 inches right now. But in order to relate back to the table, the height of the table, we subtract 2. We apply the inverse of that function to get back to the height of Timmy before the statement. Is that okay? All right. So this is cool because now we can say whatever we knew about v, that's basically what we know about f inverse applied to v. The current v, the v that is after line n's execution. Does that make sense to you?
Yes.
We knew something about v prior to line n, okay? We say, oh, v relates to this, it relates to that, blah, 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 okay? And then we execute line n. Line n changes v in a particular way. But it is undoable because function f has an inverse. So after the change, v is probably not the same as before, okay? And then what can we say about v? What do we know about v? Well, technically, we don't know anything about v anymore, but whatever we knew about v would now be applicable to f inverse of v. Okay? So is the general concept okay? I mean, do we understand the general idea of how this works? Okay. So now I can give you a concrete example to apply what we have just learned here. Okay? So here's a concrete example. The concrete example is we are on line 132, and on that line we have variable x getting, I can make this complex, I can make this simple. Let's go with simple first. So we say x gets 2 times x. Okay. And then I tell you what is the precondition, and this time it is going to be concrete, which is basically saying, okay, for whatever reason, we know x does equal to k, and x is less than y, and x is greater than z. Okay, that's what we knew about x immediately before line 32 executes. Don't ask me why it is exactly this condition, because that has to do with the 131 lines before that. We doing okay so far with the assumption? So we don't question the assumption, we just say that, yeah, for whatever reason, this is what we know that has to be true before line 132 executes. So now the question is, after line 132 executes, immediately right after that, what do we know at that point?
X divided by 2 equals k, x divided by 2 is less than y.
Exactly. Very good. So x divided by 2 would still equal to k, wouldn't it? Because compared to before line 132 executes, x is now twice as much as before. But if I divide it by half, by 2, then we get back to the old value of x. Is that okay? And what else do we know? Well, everywhere you see x, replace it with x divided by 2. Does that make sense? Yes?
So it's just basically the same thing. We're just dividing x by 2, right? Because all the
Yes. We are only adjusting x, we are replacing x with x divided by 2 because x has been doubled. Yep.
How come the post is the inverse of what it is?
Because you're undoing.
You're undoing it?
Yes. So x is the result of doing, and then f inverse is undoing what you just did. So you get back to the original value of x. Is that okay? All right. So we want to turn this into a template, don't we? Because whenever we have a chance to turn something into a template, we turn it into a template. So this way, we just have to look at a statement and ask, which template does it fit? Oh, it fit this particular one. Okay. Then we look at the concrete case, and then we say, okay, this is the line number, this is the variable being changed, da 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 da. Then we just blindly apply the template. Then it becomes just a matter of looking at the scenario, match it with one of the templates, figure out what we need to do in that case, and then blindly carry out the operation mechanically. Okay, so let's go ahead and see what we can do to generalize this and make it a template. All right. So what we do now is we get back to this part here and we say post of n. This is my notation. You may or may not be able to find it somewhere else on the internet. And what I do is I use a substitution operation, and I just abbreviate it with sub. You guys are more than welcome to spell out substitution all the time. I'm just going to stick with sub, S-U-B. Okay? So substitution takes three things. The first thing is to specify what was the original thing. Okay, what are we changing? Because substitution is a modification method, so we're changing something. What we are changing is just pre-n. In other words, we take a look at the precondition of line n, and we say, we potentially are going to do some changes here. Okay? The second thing you have to specify is to say, what are we replacing? What are we looking for to replace? We are looking for the variable being changed to replace. So in this case, in this general case, it would be v. So we are looking for the variable on the left-hand side of the assignment. And what are we replacing it with? What do you think? Why do we go through that whole long discussion of inverse functions? So we can use it here. So what do you think we are replacing v with? F inverse of v. Okay, so it's F inverse of v. And that's it. This is a template. It tells you what to do. What are the requirements to apply this template? There are a few requirements. First of all, the line has to be an assignment statement. Okay, so this does not apply to any other types of statement except for assignment statements. But there's a little bit more. The right-hand side of the assignment statement has to be a function of the variable on the left-hand side. Is that okay? In other words, it probably has to mention the variable on the left-hand side, okay? But it also has to have an inverse function. Just because it is a function doesn't mean it has an inverse. I will show you some functions that do not have inverse. Is that okay? So I'll write down the three requirements in order to apply this template. The first requirement is it has to be an assignment operation. That's pretty easy to check, because if you see a variable and then a left arrow, that pretty much tells you it's an assignment statement. Okay, easy peasy. Two, there's a function f, on the right-hand side. That's not difficult either. Any expression can be seen as a function. The last one is a little bit harder. F inverse exists. Okay? So those are the requirements in order to apply this template. So at this point, we're going to go through some examples, okay, just to find out, okay, what are you talking about, substitution, blah, 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 blah. Okay, so we're going to use line 132 again, to apply that, to see how it fits the template. Is that okay? All right, so we look at line 132, and we ask the first question, is this an assignment statement? Do we see the left arrow symbol? Yes? No?
Yes.
Yes. Okay. So checked, right? Line 2. On the right-hand side, can we see it as a function? Yeah, definitely. I mean, you can define, this time you define f of x to be 2x. Are we good? The third one requires a little bit of math or sense of math. Can we undo doubling something? Yeah, if you double something, we can undo it by multiplying that thing by 0.5 or dividing it by 2, however you want to call that, right? So it meets the third requirement as well, which means there's an inverse function. Are we good? Okay, so let's see how we can write this out. How I want you to write out, a proof, like not a proof, but a step like this. Okay. So we say, first of all, we define what is f of x. F of x is 2x. This part is pretty easy. All we do is we look at the right-hand side of the function and define that to be the function. We look at the right-hand side expression and define that to be the function. Is that okay? And then we say, well, we can find the inverse of this because x divided by 2 is an inverse function of 2x. So this is the part that takes a little bit of math, okay, but not a whole lot. In this class, we typically only deal with multiplication and addition by a constant, so it's not really that hard to reverse an operation, okay? But because it does have an inverse function, now we can apply the rule, the template. So if you look up the template, we basically say the post condition of line 132 is, okay, so this is just a copy of the template itself. It's a substitution operation. And what are we starting with? We are starting with the precondition of line 132. What are we looking for? We are looking for the variable on the left-hand side of the assignment. And on line 132, which variable is that? X. Okay, very good. So this is really important. You have to name the variable on the left-hand side, okay, as the thing that you're looking for. And what are we replacing x with? X divided by 2. But at this point, I'm not even going to say x divided by 2. I'm just going to say f inverse applied to x, to emphasize that we are undoing something that we just did to x. Is that okay? This is what I want you to write if I ask you a question about the pre and post condition of an assignment statement. This is what I want you to write. Okay? You say, do we have a function? Yes. Does the function have an inverse? Yes. Then we apply the substitution operation. And this is the template of applying the substitution operation. Doesn't seem to be very helpful. Well, it's not going to be helpful unless we spell out every single term in the substitution. So now the second line is going to be quite tedious because now we say sub, and then in place of pre-132, we copy and paste the precondition of line 132. Do we know that? Yes. It's given to us. Okay, so we just copy and paste that whole thing. So we say the expression that we are working on is x equals k and x is less than y and x is greater than z. Oops, greater than, all right, fine. Greater than z. Okay, we are looking for x and we are going to replace x with the inverse function f on x, which is x divided by 2. So this is the second line, which spells out all of those terms. And then the third line is going to be the result of the substitution. In other words, we go through this thing here, we look for this thing, and every time we find it, we replace it with this thing. Are we doing okay so far with the 3 items that we specify in a substitution operation? Okay? So we end up with something like this. We end up with x divided by 2 is k, and x divided by 2 is less than y, and x divided by 2 is greater than z. We're done. Now, if you want to push a little bit more and say, oh, but that's saying the same thing as x is 2k, that's fine. If you want to do some algebra and express these relationships a little bit differently, that's okay. Not a problem. But this is the bottom line. This is how we apply a substitution operation. Do we have any questions about this slide here? All of the same thing is also in the notes. It's just that I talk about it in class, and that may be slightly different. Yep.
Next final half is the x divided by 2 in the previous section. When we do the substitution.
Say that one more time. Sorry.
So what's happening with the additional x divided by 2 in the previous step?
You mean here?
Yeah.
So in this step, what it does in the previous step is just expansion. In other words, what it does is to say this pre-thing is expanded into this expression here. F inverse applied to x is really just x is x divided by 2. So you have to figure out that the inverse function is divided by 2 first before you can carry out this operation. Why is it not carry over to the third step? Because the transition between the second step and the third step is the actual substitution operation. So in other words, we are just manually going through this expression and say, I find a k here, I find the x here, replace it with x divided by 2. I find the x here, replace it with x divided by 2. I find another x here, replace it with x divided by 2. Is that okay? So from the first line to the second line, it's just an expansion. From the second line to the third line, it is the actual operation of how we substitute something. Okay. So are we doing okay so far with this? Yes? But this is kind of cool because it tells us that if you can tell me a precondition of an assignment statement, we are not losing anything. I can tell you what is the post condition. If you can relate 6 variables, okay, as a precondition, I can maintain, I can derive a new relationship between the 6 variables, but we are not losing anything. Okay? Yeah, this has to do with my cable being loose, and it's under tension. The connector is loose, but the cable is under tension, so it loses connection occasionally. It doesn't affect the recording, so recording is still good. Are we doing okay so far with these concepts? But then so some of you is going to ask the question. Let me scroll back a little bit. So some of you is going to have this mental question in your head, which is, what if F inverse does not exist? Then we cannot do it. If we cannot do it, then what do we do? Okay, so that becomes the next question. So in order to answer that question, the first thing I'm going to do is to show you some function that has no inverse. Okay. Is that a function? Yeah, it is a function. Okay. Give me any x, I'll give you an answer of 0. It is still a function. Technically speaking, in a math class, it is a function. But the question is, does it have an inverse? It does not have an inverse. Why doesn't it have an inverse? Because knowing the result is 0 doesn't give me anything that I can use to say oh, it was this before the operation. Is that okay? So let me just emphasize that this has no inverse. It's not reversible. Okay? What else is not reversible? Okay, something that looks reversible is also not reversible. So let me look at another function f, and this time we define it to be x minus x. Well, I mean, this one mentions x, right? So it seems like, maybe it has an inverse. No, it doesn't have an inverse either. Okay? So this one also has no inverse. Yep.
Why does the second one not have an inverse? I thought the inverse was like the opposite. So wouldn't you just add x to the second one, x plus x? Would that be the inverse?
No, because x minus x is 0. Right? So one way to think about this is, okay, let's say I choose x to be 5, okay? You just look at the result of the function. 5 minus 5 is 0. So you only know about the result is 0. If I go back to ask you the question of what was x before this operation, you cannot reverse it because every number maps to the same result. So if I only give you the result, you cannot reverse back and say what was the original value of x, because it could have been anything. Is that okay? But in this class, we're not going to use terms like injection and surjection and bijection. Those are terms referring to whether a function has properties of a function. Those concepts will be in CISP 440, okay, big time, okay? But in this class, we're not going to say that, okay? In this class, we just say, intuitively, does this function have an inverse? Has anyone taken a calculus class? Okay, some of you, okay. So I do want to relate this to some concepts that you have already known. The reason why I do this is because if you relate concepts between classes, then you can be taking 3 classes, but the actual amount of studying and understanding may be only of that of 2.5 classes, or even just 2 classes. Because the more you can relate between classes, the less you have to study, because classes have common stuff. Okay, so I'll give you, this thing. If you don't know calculus and you do not know what I'm talking about, it's okay. It won't be on the test. Okay. So in calculus and also in just in math, okay, this is x and this is function f of x. Okay, different axes, right? So the idea is, if you have something that looks, oh, okay, that the last bit just blew it. If you have something that looks like this, it is reversible. What do I mean by it's reversible? It means if I give you a point, okay, and if I just give you the height of a point, okay, so if I just specify a height over here, and I ask you what value of x will get me that height, can you find it? You just need a ruler, don't you? You use a ruler and you say, okay, it's going to be here. So this value of x will give me that, f of x value. Is that okay? But what happens when you have f of x being 5? Let's take a look. Oh, okay, let's do page new after. Okay. So you have x again, you have f of x here, and f of x is 5 is this. That's the curve. That's the quote-unquote curve, even though it's just a flat line, right? So if I say, I'm interested in something that will give me a f value of 5, okay? Can you tell me a single value of x that will give me that? You cannot, because there are many to choose from. Is that okay? Okay? Are we okay with this concept? More or less? Okay? So some of you may be thinking, all of this discussion of math and abstract stuff is not going to be useful when I'm actually coding. Okay, if I'm actually writing programs, none of this is actually going to be helpful. Well, I cannot disagree anymore. Okay? I cannot disagree because when you debug, okay, think of a scenario, okay? If you are going to become a developer or a programmer or a software engineer, you will encounter programs that do not behave as expected. Yes? Okay? What do you do when you are a developer and the program that you are developing is not behaving the way you want it to behave? So the question is, what do you do? Hmm?
Make a new program.
Write a new program?
Yeah. If it's not working, you just make
What if that program already has 1,000,000 lines and the code that you just added did not work? Debug it. Okay, troubleshoot, debug it, right? All right, so how do we troubleshoot a program? This is a big topic. Not only in this class, but in every single class, it should be talked about, okay? How do you debug a program? Yes?
Usually the IDE will tell you on which line there's a problem.
Sorry, I couldn't hear you.
Usually the IDE will tell you on which line there could be an issue.
Okay, so usually the IDE will tell you, what is wrong and on which line. Okay, so we got an acronym here, okay, IDE. IDE stands for Integrated Development Environment, okay, IDE, which is basically the a GUI, okay, a graphical user interface, that has that can show you the code, and it can show you the execution of the code. It can show you the values of the variables and so on. So you're correct, okay. An IDE can be helpful in this process, but let's say your program crashes, okay. It's not even reporting an error. The program has already been deployed, and it just crashes hard, okay. Gives you a segmentation fault in Linux or a how do you call that? Exception. How do you call it when a Windows program crashes? It pops up a little message. I cannot remember. Huh? 404 is page not found when you're trying to look for a page. Okay, but anyway, let's say your program crashes. Then what do you do?
Inspection?
Inspection. Yes. So when a program crashes, it can potentially leave behind what we call a core dump. Okay? So a core dump is basically a snapshot of the program right at the moment that it crashed, right at the moment that it totally misbehaves and the system says, nope, you cannot run any further because you have just stepped on something that you're not supposed to. Okay? So the core dump would include the values of all the variables in your program. Are we doing okay so far? So you have a snapshot of how the program died. Is that okay? Then what do you do with that core dump? So let's say that you're lucky enough that not only does it tell you the values of all the variables, it also tells you which line was the last line that they executed. Is that okay? So now you have two pieces of information. Time of death, which is the line number, and also the carcass, which is the values of all the variables. So what do? You do an autopsy. Okay? But how do you do an autopsy on a program? Proofs, very good. And exactly what do? We execute the program backwards. The program crashes on line 166, okay? You know the values of all the variables on line 166. You undo everything and you say, what got me here? You start with the post condition of a line and you're trying to go backwards to try to figure out what is the precondition of that line. Is that okay? So if you keep applying this technique and go back in the program, if you're lucky, you might go to one particular place and go like, I think this is not supposed to happen. Okay, I made the wrong decision, with this, conditional statement. I should have gone over here, but the program said to go over here. You just found your bug. Okay? So now the question is, How do we execute a program backwards? Inverse functions. Okay? Because when you look at the carcass, when you look at the core dump, that is the updated value of the variables. Okay? So if you apply the inverse function, then you have just figured out what it was right before that line. And then you use that as the post condition of the line before. You apply the same technique, and then you can go back one more line, go back one more line, go back one more line. Now the question is, well, does this method have a limit? The answer is yes, absolutely. There are times, or situations where you can back up. But if you get to a statement where the right-hand side is a function that has no inverse, then you don't know how to work with that anymore, because you do not know the value of the variable prior to that. Okay, so if you keep going backward, you will tend to lose information or relationship between the variables gradually. So at some point you might lose all information. Okay, but it will get you back to a certain point. In other words, it will get you back to a certain point and go like, yes, for sure, if I crash down here, I would have been here first with these specific values in those variables. Okay, then you can design experiments to test the program to try to resolve. Okay, I know 2 or 3 different ways I can end up here. Let me see which way got me over there. So you can design test cases to help you troubleshoot. Yes.
So you said you're gonna have to run the program backwards, right? So you're gonna find the inverse function. Would you have to do that manually or like?
Yes, you have to do it manually. There are no tools that I know of that can do it automatically for you.
So if there's like, say you said 1 million lines of code, you have to go each, like, you have to do it.
In a way, yes.
So what if the error is on like line 166 and there's like 1 million lines?
So the million of lines, okay, so that's a very interesting question. Let me just kind of repeat the question because I want it to be recorded. So the question is, if the program has 1 million lines and it crashes on a particular line, isn't that really bad because you have to execute the program backward, potentially a million times, right? So the idea is you do not want to have you don't want to write a program where you write 1 million lines before you test it the first time. Let me try to use a automotive analogy, because we all have cars that will kind of in time will have problems with cars, right? So the question is, before I'm going to pick on a particular manufacturer here. Okay, let's say Honda. Okay, so before Honda puts a car on a dealership's lot, okay, what do? Do you think they just kind of manufacture the car and then put everything together and then then they will put it onto the dealer's lot? They would test it, right? So they would have unit tests. Okay, so the first thing is, let's say we're just talking about a windshield wiper motor. Okay, because the windshield wiper has got the motor, the armitage, the wiper blade itself. There's a whole lot of components, right? So let's just talk about the windshield wiper motor. Do you think whoever is making the windshield wiper motor would just manufacture the thing and then put it into a box and ship it out to Honda? No. What do you think they would do? They would test it first, right? So they would test it at the rated voltage, check the torque, make sure it is within tolerance, right? They would check the rotation of the axle, make sure it's not off axis, within tolerance, right? So they would also kind of do a test on temperature too. So they would run the motor for X minutes and check the temperature. Is it getting too hot? So they would have a list of things to go through before the motor is even shipped to Honda. So that applies to software testing too. So how often should you test your programs? Because after this class, many of you, or all of you, will move on to cisp300, where you'll be writing actual programs. And I think in 360, the longest program that you'll be writing probably will be in the range of, I would say, maybe 200 to 300 lines. Okay, those are tiny baby programs. So the question is, are you going to write 300 lines of code, cross your fingers, and say, I hope this works? If not, you guys are laughing, so you know that's not the right answer. So what are you going to do? Your program has a total of 300 lines or so. So how do you write the program and how do you test the program so you don't get crazy when the program doesn't work? You should test small units of the program individually. Okay? Now, we haven't talked about functions yet, so I cannot really talk about that. But you basically perform small unit tests of your program. Okay? So let's say you just wrote 7, 10 lines of code, okay, and it's kind of on its own, it's a small unit. What do? You test that first. You give it test cases, and make sure that part is working. Then you write another part of the program, let's say another 15 lines of code or whatever, okay? You test that portion, okay? You write another 8 lines of code, you test that portion. So every time you test your program, you're only adding about 8 to 10 lines of code. What if I now write another 3 lines of code and now the program is totally broken? What am I going to do? Do I suspect the 200 lines of code that I have written already? Or do I suspect the 3 lines that I just added? I would probably suspect those 3 lines first. And there's a very high probability that it is really just one of those 3 lines that's causing the program to crash. So is that answering your question? Yeah. Okay. So I'm hoping that in all the future classes, like 360, 400, 430, and so on, they will continue to talk about how you write programs and how you debug programs, because it's a really big topic, and if we don't talk about it at this level, by the time you get out there to become a developer, you'll go like, okay, this is not working. What am I going to do? So I'm going to tell you some stories of when I was a TA at UC Davis, of a class that's equivalent to our 400 class here. Okay, so it's object-oriented programming. People were giving homework assignments, and I was a TA, and a TA has to go to a computer lab to help students. So when students, when their programs do not work, when they have questions, I will be the person there to help out and go like, okay, let me see what I can do with this, helping you debug a program. So there are many cases when, okay, the program is due at midnight, so it's about 10 p.m. I'll be at the lab. There'll be a lot of people panicking, and I will be observing people of how they fix their programs, debug their programs. Can you guys imagine what they do to, quote unquote, debug a program? Yes?
Usually, aren't you getting small portions of the code trying to fix?
But that would be the right way of doing it. That would be the right way of doing it. I have seen too many people just making random changes to the program and hoping that one of those random changes would fix the problem. What do you think usually would happen if people use this approach to, quote unquote, debug a program? Make it worse. Exactly. It's kind of like, your car is not working, okay? It's not starting, okay? Then you start to look under the hood and go like, maybe if I just rewire these things, the car will start working now. You start to pull off the spark plugs and then start to plug them in different orders, hoping that maybe one of these things will help fix the problem. Do you think that's going to fix the problem? No. You take the hose from your windshield wiper fluid and exchange it with brake fluid. Is that going to fix the problem? Is it going to fix any problem? No. So don't do that, okay? Do not just make random changes. Every time you make a change, there has to be a reason, okay? All right. So I'm kind of moving away from the main topic, but can you guys see how this kind of derivation is actually useful when you're writing programs? Okay? Very good. Because I was afraid that somebody is going to raise his or her hand and say, But tech, I never make mistakes. There will be no bug in any of the programs that I will ever write. So none of this applies to me. You just wasted my time. So good thing nobody said that. Somebody might be thinking about it but didn't say it. Okay, so now the question is, what if we have something like this? Okay, I'll give you a concrete example first, and then we'll talk about how to deal with it. So the concrete example is on line 61, we have a statement that looks like this. Okay, y gets 0. Okay, happens all the time because we want to reinitialize variables to specific values and then move on to do something else. Okay, and I'll even tell you what is the precondition of line 61. This is given to us, don't ask why. So before this, we know y is k plus 16, and y is greater than x, and y is less than w plus 10. Okay. Okay, so for whatever reason, okay, on line 61, right before line 61 executes, I know this condition has to be true. It is a precondition, okay? Are we good? Oh, let me add one more, just one more, because it is kind of important. Okay, so we also know that x is greater than 10. Okay, there we go. Sort of random, but it has to be there to illustrate the point. Okay. What do you think we can say about post 61? Okay. I'm not telling you what k is, okay? So do you think we can maintain this condition that y equals to k plus 16? We can't really say that anymore. We cannot say that for sure. So we have to cross it out. What about x is greater than x? It cannot be greater than x anymore, is it? Can it? Well, first of all, we don't know what y was that it was greater than x. But if I look at this here, x is greater than 10 and y is greater than x, that says y is greater than 10 for sure. Okay? I just reinitialized it to 0. So I cannot maintain that relationship anymore. So I have to cross this out. What about this one? Did I say anything about w, the value of w? Okay, you can argue and say that maybe after y get reinitialized to 0, we still satisfy this requirement. Yes, maybe, but can we guarantee it? No, we cannot guarantee it. If you cannot guarantee it, cross it out. Okay? What about the last one? X is greater than 10. Can we maintain that one? Yeah, because that statement has nothing to do with y. So I can change y all we want, but it's not going to affect x, the fact that x is greater than 10. Does that make any sense? So I am going to leave a few things here, okay? And then we'll just get down to the conclusion. And the conclusion is pretty simple. We only have this much left. The rest, we have to get rid of. Are we doing okay so far with this? Does everybody understand why we are losing items in the condition? Okay? So now the question is, well, but we like to turn this into a template. What kind of template are we talking about? The template is going to look like this. The post condition of an assignment statement where the right-hand side considered as a function that has no inverse function is going to be the result of applying what I call a forget operation. Okay? Oh, by the way, there's one more thing that we can say. Don't you think we can now say this for sure? Yeah? Okay. So the first thing we do is we perform a forget operation. From what are we forgetting something? Okay, from the precondition of the same line, we're going to forget something. What are we forgetting? We're going to forget everything that mentions the variable on the left-hand side of the assignment, because that is the variable being changed. So in this case, it is variable y. Okay, so after we forget, we might retain something, we might lose everything, doesn't matter. But we can also say from now on, we know one thing, which is y has to equal to the right-hand side. And in this case, the right-hand side is just a constant of 0, so we can just say that. Is that okay? Does everybody understand why we need to get rid of something, which is the forget operation? And why we can now say, yeah, after line 61, we know that y does equal to 0, because that's what that line does. Okay, so the second line is an expansion of the forget. So we just say, okay, we'll repeat certain portions of the previous line, except the precondition is now expanded. So the precondition is that long thing. So we're going to rewrite the whole thing. Y is k plus 16, and y is greater than x, and y is less than w, and, oh, plus 10. Okay, let me go back a little bit. And x is greater than 10. That is the first item that we supply to forget. The second item we supply to forget is the variable on the left-hand side, which in this case is y. And don't forget the end on the outside of forget, y equals to 0 in this case.
Why
So
are we forgetting the 10 is larger than, the x is larger than 10?
we are, okay, so this is the original thing. We are only forgetting the terms that contains y. Is that okay? So this is really just a mechanical way of saying, okay, we have analyzed the assignment statement, and we can now derive a post condition given the precondition. Is that okay? So we have already addressed most of the statements that we have talked about. Okay, we talked about the conditional statement. Do you remember the template from last time, the conditional statement? We got that. We got the assignment statement. The assignment statement has two branches, right? If the right-hand side is reversible, we use substitution. If it's not reversible, we use forget. Okay? Aren't there two more statement types that we have talked about? Loops. Loops, okay? So we talked about the pre-checking loop, which is a while loop, and we also talked about the post-checking loop, which is a repeat until, right? So we want to look into those as well and find out, okay, how do we figure out, the pre and post conditions of a loop? But before we move on, I just want to make sure that this is all okay for us. Yes? Okay. So loops are very tricky. Okay? So the first thing we'll do is we'll draw a picture of a while loop, and then we'll point out why it is so tricky. So we'll draw a map of a loop first, because visualizing a loop using a picture is going to be very helpful in this case. Okay, this is a while loop. So we have some kind of operation here, and after this operation we go back to the beginning to re-evaluate a condition. The condition has two branches, so there's some kind of condition here. The true branch goes here. The false branch will get us out of the loop here. This is the false branch. This is a condition. Okay, I hope this looks like a while loop that we have seen from previous classes. So the question is, why is this difficult to analyze? It has to do with a loop, because the post condition here becomes a part of the precondition. So it's kind of a chicken and egg issue. Okay? Sorry? The egg comes first. Then where did it come from? The supermarket. Or we wait for Easter. All right, so this is the shape of a loop, and I'll give you, something to analyze, okay? So this is the loop that we want to analyze. So we say while x is less than some k, do the following. X gets x plus 1, and while, okay? So this is the loop, and we'll even give it line numbers, okay? So we'll give it some line numbers. We'll say line 1 is here, line 2 is here, and line 3 is here. Okay. So how do we analyze this? So regardless of how we want to label things, let's go ahead and map out where is post 3, where is pre 2, blah blah blah, and so on. Okay. Where do you think is line 2? If you look at the construct of a while loop, in the picture, whatever we do inside the loop, where is it in this picture? The block, right? The square block or the rectangular block is line 2. Okay, you're absolutely correct. This is line 2. Line 2 goes right here. X gets x plus 1. Okay, and the condition is C. So instead of looking at this as C, we just say, okay, x is less than k is the condition. Are we good so far? So now the question is, this is post 2, don't you think? Because it's right after line 2 executes. Okay, so we'll label it. This is post 2, not too bad. And this is going to be post 3, because this is after line 3, which is basically saying, after the entire loop is done, what is the condition? This part here is pre-1. Okay, what is the condition that has to be true right before the loop starts? Are we doing okay so far with labeling, all of these specific places? What is difficult for us to do is pre-2. Because pre-2, there are several cases to get to that point, right? The first time we get here is only because pre-1 is true and the condition is true and we end up here. But in subsequent iterations, we get here because we have looped back to get here. So that means pre-2 also can potentially depend on post-2. Okay? So let's go ahead and see how we can express that. Okay, so we know that this is pre-2. The question is, how do we express it? So let's go ahead and say, what is pre-2? Okay, let me fix that. Pre-2. Okay, what can it possibly be? One thing we know for sure about pre-2 is what? That's one thing we know for sure. It has to be true. X is less than k, because whatever this condition is has to be true when we get to pre-2. So that's one thing we know for sure has to be true. So let's write it down. So we say x is less than k has to be true. What else do we know? Well, if this is the first time we get to line 2, that means pre-1 has to be true too. Because between pre-2 and pre-1, there's nothing in between that can change the value of any variable. So whatever condition that has to be true before line 1 still has to be true at least this time right before line 2 executes. Does that make sense? Yes? Okay. So we say pre-1. This is not a problem, okay? But since there's a merge, right? See, this is a merge here. Every time we see a merge in your head, you think or, okay? Because we can end up here because we just came here the first time, or we have just completed one iteration and we got back to this position. Is that okay? So that means there's an or, and the or is ORing post 2. Is that okay? Do you guys see we have a little bit of an issue here? The precondition of line 2 depends also on the post post condition of the same line, at least potentially. Okay, so in this case, it's not difficult to figure out what is post 2 if we know what pre 2 is. Because what does this look like? If we only focus on line 2, did we learn anything today so that if I tell you exactly what is pre 2, you can derive what is post 2? Did we describe a template where line 2 fits into? Exactly. So what we talked about today, earlier was, oh, here's a template. Look at the right-hand side as a function. No problem. Okay, first of all, is it an assignment statement? That's one. Okay, yes, it is. Two, if I look at the right-hand side as a function, can I look at the right-hand side as a function? Yes. Does that function have an inverse? F of x is x plus 1, has an inverse function of f inverse of x is x minus 1. It meets all three requirements. We can apply the forget or substitution method, and then we can derive the post condition. Easy peasy, right? We replace all occurrences of x in the condition with x minus 1. Done. The problem is, so let me just write it here. So post 2, okay, we can now say, oh, okay, we need to apply the substitution operation. Whatever in pre 2, whatever occurrence of x we have in pre 2, change it to x minus 1. Okay? No problem. We got this figured out. The problem is, post 2 appears back here. So now it becomes a quote-unquote chicken and egg problem, because if I don't know post 2, I cannot express pre 2. If I cannot express pre 2, I cannot derive post 2. And it becomes cyclic. Is that okay? Does everybody understand, what kind of a situation we got into? So it's a little bit difficult. So now the question is, well, but in this case, how do we fix this problem? Well, to fix this problem, we have to identify, and there's no mechanical method to do this. We have to identify what we call gosh, I cannot remember the term. It's in the notes. Something condition. Okay, let me cheat and read my notes. You guys know that eventually I have to read my notes, right? Loop-Invariant, that's it. Okay. I actually did not read the notes, it's just that I just suddenly remember. It's called a Loop-Invariant. Okay, so a Loop-Invariant is a condition, but what do you think is special about that condition? Okay, we know it has something about loop because the name is Loop-Invariant. But what does invariant mean? In usually means not, right? Negate. Vary, V-A-R-I, means change. And ANT is just turning into an adjective, okay? So that means it's a condition that does not change in the loop. That condition is true as a precondition. That condition is also true as a post condition. So we are looking for a loop invariant condition. Once we identify the loop invariant, the rest will fall in place. I cannot explain that process in 2 minutes. So, so this is going to be something that we talk about next week. But we'll also talk about the practice exam for exam 1 next week, because we are getting close to week 5, so the first exam is going to be coming up. Okay, so read ahead of me and make sure that you understand all of the material that we have worked on up to this point. I do not have any actual homework assignment at this point because I need to get this stuff through first. Okay. Hold on a second. Let me Let me turn off the recorder first. Yeah. I can't even click it because all the people walking
Yeah.
makes it kind of hard